Welcome to the explanation of tree traversals. In this lesson, we'll explore the fundamental concepts of tree traversals, specifically inorder, preorder, and postorder traversals. These methods allow us to systematically visit each node in a tree, which is a crucial skill for many tree-based algorithms and data manipulations. Let's get started. Let's define the basic structure of a tree before diving into tree traversals. A tree is a hierarchical data structure consisting of nodes connected by edges. Each node contains a value and references to its child nodes. A binary tree is a specific type of tree where each node has at most two children, referred to as the left child and the right child. Tree traversal is the process of visiting each node in the tree, exactly once in a specific order. The image shows node structure and a sample tree structure to understand traversal better. Now let's discuss the three primary types of tree traversals: inorder, preorder, and postorder. In inorder traversal, we visit the left subtree first, then the root, and finally the right subtree. This order is typically represented as left, root, right. In preorder traversal, we start by visiting the root followed by the left subtree, and then the right subtree represented as root, left, right. Lastly, in postorder traversal, we visit the left subtree, then the right subtree, and finally the root represented as left, right, root. The order of traversal is different for all three. Inorder traversal would be D, B, E, A, F, C. Preorder traversal would be A, B, D, C, F. Postorder traversal would be D, B, F, C. The tree structure is kept the same for all traversal methods. Let's take a closer look at the inorder traversal technique. The process involves traversing the left subtree, visiting the root, and then traversing the right subtree. This is often referred to as left, root, right. The code snippet provides a clear implementation of the inorder traversal using recursion. Initially, we check if the root is null. If so, we return an empty list. Next, we recursively traverse the left subtree and extend the result with the nodes visited. Then, we visit the root by appending its value to the result. Lastly, we recursively traverse the right subtree and extend the result again. The visualization on the right shows the order in which the nodes are visited during an inorder traversal, resulting in the sequence D, B, E, A, F, C. Now let's explore preorder traversal. In this method, we visit the root first, then traverse the left subtree followed by the right subtree. This order is root, left, right. The code snippet offers a clear implementation of preorder traversal using recursion. We start by checking if the root is null. If it is, we return an empty list. We then visit the root by appending its value to the result. Next, we recursively traverse the left subtree and extend the result. Finally, we recursively traverse the right subtree and extend the result again. The visualization illustrates the sequence in which the nodes are visited during a preorder traversal, resulting in the sequence A, B, D, C, F. Now let's dive into postorder traversal. Here we traverse the left subtree, then the right subtree, and finally visit the root. This order is left, right, root. The code snippet illustrates the implementation of postorder traversal using recursion. We begin by checking if the root is null. If so, we return an empty list. Then we recursively traverse the left subtree and extend the result. Next, we recursively traverse the right subtree and extend the result again. Finally, we visit the root by appending its value to the result. The visualization demonstrates the order in which the nodes are visited during a postorder traversal, resulting in the sequence D, B, F, C. Let's explore some practical applications of tree traversals. Inorder traversal is commonly used for binary search tree validation, providing a sorted order of elements in a BST, tree flattening for storage, and evaluating expressions in expression trees. Preorder traversal is useful for creating a copy of the tree, evaluating prefix expressions, serializing tree structures, and displaying directory structures. Postorder traversal is effective for deleting a tree, evaluating postfix expressions, performing bottom-up calculations, and resolving dependencies. These applications highlight the versatility and importance of tree traversals in various algorithms and data manipulations. Now let's compare the implementation approaches of tree traversals, specifically recursive versus iterative methods. The recursive implementation is simple and intuitive, offering clean code and natural tree traversal. However, it comes with call stack overhead, a risk of stack overflow, and can be memory intensive. On the other hand, the iterative implementation avoids recursion overhead, provides better space complexity, and offers more explicit control. However, it involves more complex logic, is less intuitive, and can be harder to implement. Both methods have their own trade-offs, so the choice depends on the specific requirements and constraints of the task. In summary, tree traversals are fundamental algorithms for processing tree data structures, enabling systematic access to each node. Inorder Traversal is essential for sorted access in binary search trees. Preorder Traversal is useful for creating tree copies and prefix expressions. Postorder Traversal is effective for tree deletion and expression evaluation. Both recursive and iterative implementations have their own trade-offs, so the choice depends on the specific requirements. Understanding traversal patterns is essential for efficient tree operations and many algorithms. The diagram shows different traversal patterns. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.